Hello, good morning. If someone could just say in chat if they can hear me, that would be super helpful because I haven't. Okay, awesome. Cool. Now let's see if I can share my screen successfully. Yep, there we go. Cool. All right, I'll give a minute or two just for any stragglers, but welcome this morning to a robotics workshop. I'm pretty excited about this because I've done robotics workshops at several hackathons before. And it's always been very difficult to get people sort of interacting with hardware, just as a matter of it's a lot of setup and you only really have 24 hours to do something. And almost ironically, um, here at a virtual event, I think we're going to be able to get you guys to work with real robots a little easier than if you were at a physical hackathon. And I'll go into a little bit of that later. All right. So I'll go ahead and get started. First, a little bit about me. I studied mechanical engineering at Boston University. I graduated a couple of years ago. And while in Boston, I worked for two robotics startups there. One of them was Piaggio Fast Forward, where I worked on Jita, which is that little spherical yellow robot. Then I also worked for a startup called Optimus Ride. And right now I'm a software engineer at Waymo, working on the planning team. So a little bit about what we'll go through today. The first little bit is going to be like an introduction to robotics. And then, oh, can anyone else not hear me? Okay, cool. Um, Thank you. So we'll go through a little bit of an introduction, and then we'll talk about how you guys are going to be able to actually play capture the flag on real robots and sort of play capture the flag against other teams as a friendly competition. Or optionally, if you want to do something completely else, you could totally run some other multi-robot algorithm on what we'll talk about, the Robotarium, and do something completely different, which is totally cool, and I'll show you how to do that. And then at the very end, we'll go over questions. But if you have any questions, like while I'm going through the presentation, feel free to put those in the chat. I'm more than happy to answer those as we go. So what is a robot? It's kind of a loaded term. And there are some common traits that we see across different kinds of robotics. In general, most robots we see have sensors. They have some computer and they have actuators. And roughly, these are sensors to understand the world, a computer to take in that sensory input and reason about the world, and then actuators to take action within and sort of on the world. And this is a very broad description, but the overall sort of commonality is there's this relationship between the robot and the world, the robot and the state of the world, and even the robot and its own state that it holds. So a few examples of robots. These are all pretty clearly robots. You can see like a big robot arm here, obviously moving around the world, looks like a robot, smells like a robot. This over here is another great example. This is Baxter, which poor Baxter, they don't make these anymore. But it's a little robot arm that has cameras on it, has a little gripper, and you can see it's able to pick up those building blocks and move them around. And then we start to get into a startup in Boston called Spice, which they call themselves a robotic kitchen. This doesn't look as much like a robot, but you can kind of see these little drums. There's like a conveyor belt back there. There's like temperature sensors for like cooking food and stuff. So it's probably still a robot. But then like, what about robots that don't move? This is definitely a robot. Jibo is a robot. It can like swivel around like where it's sitting, but it can't really like interact with the world. It has a camera, so it can talk to you, it can hear you and stuff. But But it's definitely a robot. It doesn't necessarily need to move around in order to be a robot. But then we get into things like industrial automation. So this is like an assembly line with a bunch of motors and actuators and sensors. But I don't know if I'd necessarily call this a robot. It's kind of like an automated assembly line. It's just sort of doing a repetitive task over and over again. You could totally argue that this is a robot because it senses reasons about that and takes action just like very fast and in a very regular manner. But it's kind of up for debate. And then over here, we have a thermostat. A thermostat senses, it reasons about the world based on what temperature you've set, and it takes action. It modifies your heating and cooling. Okay, but maybe you say, well, that's not really like a robot. It's just turning the heat on if it gets too cold, and it's turning the AC on if it gets too hot. But then what about a thermostat that learns? A thermostat that actually does have some more rich like reasoning component that's saying, I'm going to learn how like my user changes temperature over time, or like when they're in the house. And it gets really sort of blurred, which is both really cool and sometimes confusing, because it's like, well, where do we sort of like draw the line of what is robotics? And I'm not really going to address that because, it's okay to sort of leave it a little ambiguous and robotics sort of be like a broad umbrella. This right here is a very large diagram that I want to go through for a somewhat modern like robotic stack. I've pulled this from NVIDIA. This is sort of a lot of their various like code that they've developed around, their robotics platform. And you can kind of see that there's this pretty significant flow from inputs that are going into this sensing block. Those sensing inputs are then going into the planning block. And that planning block is then going into the action block. And then that is finally moving actuators, these motor drivers. So to go into a little more depth, you have all these different kind of sensors here. You have depth sensors, you have RGB cameras, you have motion modules, you even have sort of microphones, touch, ultrasonic, infrared, all these different sensors that can sort of sense the world, but aren't really going to give you any rich information about it yet. This sense block is then going to do sort of a few different things. It can do sort of object recognition, face tracking, body tracking, all this different kind of stuff. And then importantly, it's going to do sensor fusion. So when we have a lot of different robots on a robot, a pretty significant step is how do we fuse all that information together to create sort of a cohesive understanding of the world. And that basically gets us our robot state, our worldview, and command inputs. This one's a little weird. I don't know why they put this block there. That, once we get an understanding of the world, now we can start to understand like what's going on in it. So we have our planner. Planners like vary significantly depending on what kind of robot you're working on. But in general, you might have something that's like a path planner. A path planner could be sort of for a mobile robot or for a robot arm, even sort of designing the path that a robot arm is going to take to get to a goal. But then you can also have sort of like a behavioral planner where you want to have the robot do certain tasks like, pick up my laundry, put it in the washer, and stuff like that. And it can sort of generate very coarse high-level tasks of, things that it needs to do in order. And then within each of those tasks, you'll have a more fine-grained planning step that says, okay, the piece of clothing is this position on the floor. I'm going to pick it up there, and I'm going to move it to XYZ, this position, to move it into the washer. And then finally, that plan is then going to go into the act module. And we'll talk about this in the context of like a controller. So an act module is basically going to take this plan, and it's going to turn it into movement, and it's going to finally hit the motor drivers and move things. Any questions before I keep going? All right, cool. So a little bit of an example. This is everyone's favorite little robot, Spot Mini. And you can see this robot in particular with the arm and the little chicken head kind of thing is a moderately complex system. So we have a lot of things going on here. First of all, we have some sensors. We have a flash LiDAR that's actually on the gripper itself. You can't see it here, but if you actually see the robot in person, you'll see a little LiDARs on there. And that's basically generating a depth map of what's immediately in front of the actuator. There's also depth sensors all around the robot. There's 2 on the front here, there's 2 on the sides, there's 2 in the back. They actually have 6 Intel RealSense D435s. I don't have insider info. You can just recognize the kind of sensor this is. It's a really cool sensor. But basically with this, they're able to map the entire area around Spot Mini, or almost all of it, in depth information. There's, of course, the brain here, which is going to be taking in all that depth information, all of this LiDAR information, and processing it, which is going to be pretty computationally intensive given the number of sensors they have. And then you have a couple actuators. You have actuators down here, the legs that are going to move the robot. You have an actuator up here, which is going to move this arm and be able to manipulate the world. And that's how it's able to sense this door handle, see, I see a door handle, grasp it, and then move it appropriately. All right, cool. So we'll go into detail about, at a moderately high level, about 4 of these. And these are sort of the main pillars that you will see in common between robots. There's obviously going to be more depending on the kind of system you're working on, but these are the ones that are like common across like a lot of different robotics. And the first one is sort of handling that sensory input and getting sensor data in. And the first thing that's important is sensors aren't perfect. They're totally not going to give you information that's perfect about the world. There's going to be noise. They're not going to be sort of, you're not going to know where they're mounted absolutely with absolute accuracy. And, they can be occluded, they can get dirty. A bunch of different things can happen with sensors, and you need to handle all of them when designing a real robot. Sensors also don't provide semantic information. So just a camera taking a picture of this isn't able to recognize, oh, that's a dog. You actually need to put it through sort of a classifier or some sort of machine learning algorithm that will then say, oh, okay, this is a dog, and add that information to the sensory input that's going to enhance sort of your understanding of the world. Another common approach is sort of semantic segmentation with RGB cameras. You can see here there's been an image that's taken, and a machine learning algorithm has gone and sort of colored the different regions that it thinks are different things. So it thinks this area over here is a sidewalk. This area right here is a road. All these people are in red, cars are in blue, and so on. And with this, it's basically able to develop a much richer understanding of the world around it. There's a wide range of sensing capabilities: RGB cameras, depth sensors, haptic sensors, ranging sensors like radar and ultrasonics, and plenty more that I haven't listed here. But overall, there's a pretty wide diversity of sensors when you're working in robotics. Then let's talk about state estimation. So once you have all this sensor data about the world, it's not very useful unless you know where the robot is, or the robot knows where itself is. So a very important aspect of robotics is how you can fuse sensor data between other sensors, or even with a single sensor over time, in order to provide a very reliable estimate of the robot, basically where the robot is in the world, or perhaps where different actuators of the robot are. So if you have a robot arm, that's going to be accurately estimating sort of where the different joints of your arm are. If it's a mobile robot or a drone, it's going to be trying to look at the world and figure out where you are in the world. And there's a couple different kind of state estimation approaches. At a very high level, there's kind of 2 categories. There are model-free state estimation approaches, and this is basically an approach that doesn't know about how the robot can move. It just sort of fuses or filters sensor data without information about, if I'm a car, or I'm a mobile robot, or I'm a drone. You can see this is a great example. This is pretty state-of-the-art work from the MIT Spark lab. It's called Chimera. And not only will it do this super advanced, this is called SLAM here, simultaneous localization and mapping. I believe with this, I think they just have a single camera that's doing this mapping. And you can see it's looking around the scene. It's projecting all this weird geometry onto it that I don't understand what it does. But you are basically developing this 3D map of the world from a single monocular camera as you move it around. And you're able to say, this little like red, green, and blue little corner here is basically the state of the camera. So it's able to estimate the state of the camera really accurately by mapping the environment and then finding itself in that environment. So this is super cool. You can also have model-based filters, and these are a lot more, I'd say, reliable, because you are filtering sensor information based on how your robot's going to move. Take, for example, if I have a robot and I know it's only going to move on the ground, I don't need to worry about sort of the Z component, how high it is off the ground. I can just say, okay, I'm going to make a robot model, and the robot doesn't fly. The Z position is 0. I'm only going to worry about X, Y. Immediately, I constrain this to a two-dimensional problem, and I can use an approach like this, which is a extended Kalman filter. And basically, there's not a lot of labels here, but what's going on is you have this blue line that's estimating the state of this robot over time, given all these noisy sensor inputs. Basically, all these little green dots are noisy data about where the robot thinks it is. And if you were to just sort of integrate integrate those data points over time, you would basically get this black state estimate that's not very accurate. You can see the real state of the robot over here, and the actual, or the just blindly integrated state, diverges significantly. But you can see this red blob and this red and blue line evolve actually pretty accurately over time and stay with the ground truth. The ground truth being sort of where the robot actually is in the world. So there's many solutions. Kalman filters, like I just mentioned, are a big one. Factor graphs are also a pretty significant area in state estimation and optimization in general. I won't go into these, but they are super interesting. There's plenty of other optimization approaches, and as we mentioned, there's SLAM, which is happening up here. How are we on time? Okay, we're good. So then let's talk about planning. So given the information about the world we've gathered, what do we want the robot to do? Generally, we're going to take all that information about the world and we're going to encode it into something called cost. And basically, cost is something, it's a heuristic that we're able to use that's going to drive a bunch of different planning algorithms. Basically, most planning algorithms are going to say, okay, given the current state of the robot and the end state that I want to get to, the goal, how do I get there while minimizing cost? And that's pretty much the entirety of the planning problem. Different algorithms are going to approach it in vastly different ways. And if you're interested in the details, I'm more than happy to go into that after this. But there's a bunch of different trade-offs that you have to account for, because there are some very limited applications where you can explore your entire possibility, or the entire range of possibilities of motion, but those are very few. If you have a 2D problem like this, it's actually it's moderately easy to sort of explore every single part of this workspace, every single part of where the robot can move, and say, yes, this is absolutely the lowest cost path that I can find from the start point to the goal. But if you all of a sudden add a third dimension, if you have a robot arm, especially where you have like 5 or 6 different actuators, it's now completely computationally infeasible to explore that entire space to get from a start to a goal. Like even with like a very powerful computer, it's impossible. So generally, we're going to encode things in cost. And basically, the more undesirable it would be to navigate in a given area, the higher the cost. So a great example is this right here, which is basically a potential planner. This is a really nice planner in that it's really simple. You can basically see we have a goal point here, and we have a start point here. And the darker the color is, the higher the cost is, and the lighter the color is, the lower the cost is. So basically, we just have this big bowl, and the robot wants to get to the bottom of the bowl. It wants to find the lowest cost point. And when doing that, it also needs to avoid these obstacles, which have been helpfully encoded as very high cost objects. So the little states of the robot then kind of find a path around those little obstacle blobs. This algorithm isn't guaranteed by any means to find the least cost path, like the globally best path, absolutely no matter what, but it's probably going to find a reasonable path. Now, there are some sort of caveats here. For example, if you were to make a wall here in kind of a U shape, this planner would probably get stuck right there because it doesn't really handle global complexity very well. It's very good at sort of figuring out, given my current state, I want to go that direction. It's not very good about saying, oh, my goal is like over this wall, and so I need to do something slightly more complex and go around the wall, and it can fail in those cases. But it's a very easy planner to implement, and for capture the flag, I'm going to suggest this is one of the first ones you try and go for because it works pretty well for the Robotarium, the setting of the robots. A few other approaches, if you're working in manipulation or with robot arms, RRT is a pretty popular planner among several others. These are roughly algorithms that are going to explore the space in planning. For a robot arm, that's going to be a 5, 6, 7 degree of freedom or dimensional space, which is very complex to explore. But if you have RRT, it's going to basically explore that in a moderately optimal way that will never generate the same path twice. But if you actually look at the papers, there are some guarantees of, if you run it forever, it'll eventually reach like the most optimal path. It's really interesting if you're interested in that. Mobile robots, many of you probably know about A-Star, which is basically a graph based planner. And you can see a little picture of that there. All those little cyan X's are basically states that A-Star is exploring as it's trying to find its way from the start point over here over to the goal point here. And you can see once it breaks that wall and finally gets there, it's very easily able to find that lowest cost path. Drones will oftentimes use one of these other planners, or it's very popular recently for them to use something called model predictive control. This is basically an optimization-based approach. So you're still going to encode things in cost, but you're going to move away from a sort of heuristic-based algorithm. Both A-Star and this potential fields algorithm are basically heuristic-based algorithms where you need to define a heuristic that's going to get your robot closer to the goal. And we can talk about that more offline if anyone's interested. But model predictive control and other optimization-based approaches are going to use sort of a much more robust optimization procedure to take in that cost information and say, this is the optimal path, given my control inputs, given my robot. You also generally are going to encode costs on your actuators. So you might not want to like gun it on your actuators. You may want to sort of have some parameter that's saying like, okay, only really heavily exert the actuators if I really need to navigate a space. Otherwise, I want to stay relatively low in my actuator limits. And then we get to the final part, which is controls. This is a pretty cool part in that controls can be very simple in like very simple cases, but they can very quickly get extremely complex. And basically, the overall goal of controls is, given the plan that the planner gave us, how do we control the robot to follow the path as best as we can? And the important thing here is we need a robot model. We need some understanding of how the robot is going to operate in the world. But this kind of runs into a problem because all models are wrong, but some are useful. So I could develop a model for like my Roomba robot that says, my Roomba robot rotates around its base, it stays on the floor, and it's just going to drive. It's totally cool. It just moves in 2 dimensions. It's never going to fly or anything like that. But then all of a sudden, my model breaks if a human comes over and picks up the robot. Because all of a sudden, I'm now in the Z dimension, and I've completely broken my model. The model doesn't know how to understand, since I just coded it to make 2D assumptions about the world. Excuse me. And so you have to basically design a controller that's robust to that kind of input, that's robust to noise in your sensors, that's robust to sort of tracking error. For example, if my robot, like, one of the motors is kind of faulty and I don't quite perfectly track my path, how do I sort of correct for that and get back onto the path and not sort of deviate from that significantly? And this is particularly difficult when dealing with nonlinear systems. And we'll go into a little bit of that. Controls, like I mentioned, they can be super simple, but depending on the robot, they can get very complex. A moderately simple approach is something like a PID controller. And that's actually shown here on the right, where you basically have some input. You have a proportional term to your error. Your error is basically your current robot state with respect to where you want the robot to be. You have some integral over that error, and then you have a derivative of how that error is changing over time. And basically, you tune three coefficients, P, I, and D. You put that into, just add those all together, and then you use that to command your robot. So you can actually write this in like very few lines of code. And if you tune it appropriately, you can get it to work really well for most systems. But it pretty much fails when you get to nonlinear systems, unless you're staying very close to a linearization point. So for nonlinear systems, we can start to get into something called a linearized quadratic regulator, or an LQR. And there's a bunch of different variants and flavors of this, but basically, this is going to take a nonlinear system, linearize it about some point, and then figure out what the optimal control is for that robot in order to correct for any error. And then finally, there's model predictive control, which we discussed in the last slide a little bit. And this is basically an optimization procedure that, given some information about our goal or like the plan, MPC can basically find the optimal control inputs given a model and send those to the robot, basically. And it's moderately robust. It was formerly very popular, well, still is, but it's very popular in like chemical processing plants. But as computers have gotten faster and faster, this is a pretty computationally intense procedure. Folks have found ways to optimize it to get it to run on robots in real time, which is super cool. Particularly a few drones are using it to basically say, I want the drone to go there. You throw it into this big blob called model predictive control. And then the output of model predictive control is literally set the motor speed for these four motors to this. So it literally is directly controlling those actuators. So awesome. A little bit of a summary. Robotics is a very broad field, but this is what makes it super exciting. We touched on sensor input, state estimation, planning, and controls. And yeah, at this point, perfect. I am right on time. Any questions about the overview, any questions about robotics? And then right after this, I'm going to go into how to use the Robotarium, how to play capture the flag, how to play capture the flag against other teams as a friendly competition, and how to interact with that code. All right, there's no questions. I'll keep going. So let's talk about the Robotarium. First, I'm going to show you a little video. I don't know if the audio goes through, but if it doesn't, that's fine. There's just music. There's no one talking. At least I don't think there is. So this is the Robotarium. It's basically an arena with all these little robots, which is super cool. And with this, you basically can command, how do the robots learn right from wrong? Do the engineers have to teach each one? That's a good question. Right and wrong is a pretty difficult concept to approach in terms of robotics. Plenty of people have written on like the morality of robots in various forms, like do robots have rights? What kind of rules do robots need to follow in order to sort of be moral? Asimov famously wrote like the three laws of robotics, which deal with, don't harm humans, don't harm thyself, and sort of the priority of each of those. But yeah, essentially you do have to sort of engineer it into the robot. So you're basically going to teach the robot, given some understanding in the world, how to respond to that stimulus. So it kind of is subjective to like our own perspective, whether or not a robot's action is right or wrong. If from the robot's perspective, it's always going to be, I did the right thing. This is sort of what the code told me to do. And that's the action I took. So, Terminator robots are just following their programming. I'm not going to get into the philosophy of that because then we could be here all day. But yeah, it's an interesting question. It's definitely interesting, especially as we talk about sort of like what the responsibility of engineers is when designing an autonomous system, and what the responsibility is to make sure that those autonomous systems are safe. So yeah, The Robotarium, to summarize this, is basically this cool test bed where you can upload algorithms and the robots will run themselves and you basically get the results. So these are each of the little robots. We'll go to this website in a second, but you can see here there's like a little Raspberry Pi. There's some distance sensors actually on here. There's some white balls on the top, and those are actually little markers. A motion capture system up above is going to, let me pause this. Motion capture system up above is going to record the state of each robot, such that you don't need to worry about noisy data, essentially. And you can just trust sort of the ground truth that you get from up above. But yeah, so the first step for us is going to be developing your idea, or basically playing capture the flag, or doing something else for your project that you so choose to do. And this is going to be essentially developing code. For us, it's going to be in a a Jupyter notebook or a Google Colab. And you're basically going to design, given the state of the world, what's the robot going to do? We'll skip a little bit here. This is the simulation API that the Robotarium provides that we'll be using, which is going to be super cool. There's a nice little animation of what the simulation looks like. So this is basically what you guys will use today and through the weekend to develop your system and sort of test it relatively rapidly. And once you get to a place where you like your code, you can then just basically submit it to the Robotarium. Some instructions that we're just going to skip for now. They're going to do some validation on your code just to make sure that it looks good. I'm going to be doing part of that as well, just so we can match teams up and make sure that things are going to operate correctly. Deploy to the actual Robotarium. So at the end of the day, what's going to happen is probably after this weekend, because I don't think they're going to run experiments this weekend, but probably next week, after you've designed your algorithm, be it for capture the flag or something else, they'll run it, and then they'll send you a video of it running. So you're basically going to see a video of all these little robots following the code that you write for them. You're going to get that video data and any other data that you need. And then, yeah, you can just iterate. Cool. So that's a little overview of like the actual test bed that we're going to use. And now let's talk about sort of the actual game. So I'm going to do something super sketchy here, and I'm going to move my computer to try and draw a little bit. Let's see if this works. Oh, sweet. That's totally going to work. Okay. All right, my laptop is very precariously perched. Hopefully you guys can still hear me. Can you guys still hear me? Yes, awesome. Okay. So basically, I'm going to talk a little bit about sort of the model for the robot and what you guys are going to work with. And I'll make sure that you guys can see my notebook. But basically, each of these little robots looks like this. It's a little box. And I don't know the dimensions off the top of my head. I believe it's like 11 centimeters by 10 centimeters, but I'll double check just to make sure. And this robot basically has two little wheels on the back that are going to be your drive wheels. And then it has this caster on the front, which basically is just a support point for it to move. And we're going to develop basically how we want to control this robot right now. You guys are welcome to sort of expand on this and develop like a more robust controller or a different controller. But basically, we want to say, given the current state of the robot, we're going to develop some notion of like the centroid of the robot. how do I get to a goal point? So the control for this robot is going to look, I'm not going to go through the derivation today, but if you're interested, just message me and we can. We're going to have, our state's going to be x, y, and theta. And so this is going to be a full description of where the robot is in the world. So given a little plot here, we have x, y, and then with respect to here, we have the robot heading theta. And then we have two control inputs. We're going to use two controls for the robot, which will be forward velocity and angular velocity. So how forward do we want to go? How angular do we want to go? And basically, the control for this robot is going to look like this. We're going to have x dot equals v cosine theta, y dot equals v sine theta, and theta dot equals omega. So basically what this is saying is, let's run through a couple examples here for what this means for an individual robot. If my robot has a heading of 0, and I commanded it some positive velocity of like 1.0 meters per second, that means x dot is going to be 1 meters per second. And if we want, we can say, okay, go forward one time step dt. And for the Robotarian, the time step is equal to 0.033 seconds. So that means after 1 dt, the new state, we're going to represent this as x n plus 1 equals x of n times v, x of n plus v cosine theta dt. Simple as that. And then y n plus 1, similarly, is going to be y of n plus v cosine theta dt. I guess I should make sure this all looks good for you guys. How do the robots learn? Okay, awesome. I can't see the chat right now because the screen is in this weird position. And then finally, theta n plus 1 equals theta of n plus omega dt. And this is basically our robot model, or to be very specific, our kinematic model. And this defines how the robot's going to move over time. Any questions before I keep going? Cool. All right. So then what we want to do is, given sort of the physical state of the robot, x, y, and theta, what you guys are basically going to do is define a policy. So what is a policy? A policy is denoted by the symbol pi, and it's going to take in the state. It's going to take in an observation that the robot makes, and it's going to result in an action. Now, for a purely physical system, the state is just going to be x, y, and theta. We'll talk about the observation in 1 second. And the action is going to be our controls. It's just going to say set v and set omega. So given the state, we have some policy that is going to act on that state and then take an action. So a very simple policy might say, if state does not equal goal, This is very rough, and this is not how you would write it in actual code. But if state does not equal goal, control, given the state and the goal, give me a command, and then return that command. So what's this doing? This is basically saying, I'm going to develop a very simple controller that says, I want to get to some goal. You know, I have a robot here, and I want it to get to some goal point here, which is going to be defined as x, y, and theta, basically some end state for the robot that we want it to get to. And I'm going to get some a velocity command, excuse me, for both linear and angular velocity out of that, and I'm going to return that. That's going to be my action. Now for capture the flag, it's going to be slightly more complex. The action is going to be v and w, or excuse me, v and omega, and it's also going to be this action that we can take called tag, and we'll go into that in a second. And we're going to have our policy that's going to operate on the state. And then let's talk about this observation. Now, the observation model for the robot is basically, for a real robot, what you would develop with the sensors that a robot might have. So given this little guy right here, you know, maybe we have this in some sort of box, and there's another robot over here. What an observation would look like for this robot is, let's say that we have a LiDAR on the front. And if you're not familiar, a LiDAR is basically, most of the time, a little spinning object that is going to send out laser beams and figure out how far away a given point is. And it's going to do that very quickly and very repeatedly in sort of this circular fashion. And what you effectively end up getting is all of these little points. So you'll get points all down this wall here. And you'll basically start to develop a model for the world, basically a 2D spatial model of the world based on this LiDAR data. That's not a point, that's a smudge. So what you'll have is you'll see sort of the edge of this robot, maybe like a little of this here. You won't be able to see the back of the robot because our visibility only sees sort of the front of it. And you'll be able to see sort of the rest of the points here. Now for the initial sort of simpler case for interacting with the Robotarian, I've basically developed an observation model for you folks. So you basically are going to get an observation that normally you would have to process these LiDAR points and say, okay, this is like a little boxy thing. I think that's a robot. Classify that as a robot. And you might fuse that with camera data to say, oh, okay, I see this robot is purple. So I know this purple robot is on the purple team. But I've just developed a simple observation model for you guys that already does this processing for you. And basically, this is going to return the robots I see and the flags I see. But it's not going to directly say, oh, this robot is at X, Y, and theta. It's going to say, this robot, with respect to the ego robot, the ego robot is basically the robot that we are. You're going to have another robot, which is distance d away. And with respect to our robot heading, oh, I actually messed this up. With respect to our robot heading, which is pointed straight forward, is some angle theta away from our robot. Okay, so any questions so far? The next step is we're going to go into the actual collaboratory and work on code. Awesome. Cool. All right, hello again. So now let's actually go in and look at what code looks like for this. I have a notebook open here. Oh, that's the solutions. Just kidding. And so this is basically what you all are going to be able to interact with and use for developing your system and developing your algorithms. So the first step here is just cloning this repository that has some base code that you're going to use. I'll give you guys access to those notebooks so you can basically just clone it and use it for yourself. This is for reference. Basically, what you all are going to design is a robot state object and a robot policy object. So the robot policy is what we just talked about. It's that function. Oh, yeah, absolutely. Let's see. Is that better? Is that readable? Okay, awesome. So basically, what we just talked about, that policy is right here. And it's totally encoded just in this function. We have a policy that, given that it's a Python class, takes in self. And it just takes in two arguments, state and observation. Now, the state is going to be an instance of this object up here called robot state, which has all of these fields that you can use when sort of designing your algorithm. And you additionally can expand this state. So I'm going to show you how you can inherit from this object and create sort of a more complex robot state. So a few sort of data points that you want to take note of here. The first is sort of the initial pose that the robot's going to start in. I'll show you sort of what the layout of the robot looks like. But this is basically information about this is where the robot started. You also have this member right here called underscore pose. This is basically going to tell you exactly where the robot is at all times. You can totally use this for prototyping. I would strongly encourage you not to use this when actually making a submission, because you're going to have to sort of go through the steps of, okay, how do I estimate the state of my robot given my sensor information, rather than just sort of directly getting the state of the robot, the physical state of the robot, that is. I'm also going to give you sort of the last velocity command that was sent to the robot. There's two teams. There's the orange team and the purple team. And so this is just going to tell you, is it team purple or is it team orange? You probably don't need to know that because you know what team you are, but this is used in other parts of the code. You're going to have a robot number. So purple team has 0 through 5, and the orange team has 6 through 11. And then capture the flag, has this idea that if you're on the opposing team's side and you're tagged, you have to go all the way back to your end. I didn't develop like a sense of a jail or anything. You basically have to go all the way back to your side of the arena, tag the wall, and then you're back in play. You as a robot yourself can tag. However, I've made it such that you can't just sort of like repeatedly spam the tag, and you have basically a cooldown. So you can tag you can try to tag every 3 seconds. Whether or not that tag succeeds or fails, you're going to have to wait 3 seconds until you can try to tag again. And this flag right here is basically something that you can access and say, am I able to tag? Try to tag. And then if you actually get to the other team's side, you capture a flag, you're going to sort of have this argument that says, do I have a flag? Right now it's false. If you get a flag, it's going to be true. Then we have the robot policy that's going to operate on that state. So basically, an instance of the state right here is going to be passed into the policy, and you're going to be able to access all of those variables. And you're also going to get in an observation. And the observation is going to look like this. There's going to be 2 lists. One of them is going to be all the flags. And this is going to give you the, oh dear. Yeah, here we go. This is going to give you the angle for each flag, basically. There's going to be a dictionary that's going to give you the angle to each flag, the distance to each flag, what the flag color is, and whether or not the flag is active. So it's going to be active if the flag is there and ready to be captured. It's going to be inactive if it's not there and one of your teammates has already gotten it, or one of your team robots has already gotten it. Then you're going to have a list of robots. For each of the robots, you're going to have an angle to that robot with respect to the robot's heading. your ego robot's heading, that is, the distance from your ego robot to this other robot, and then the color, so what team that robot is on. So with this, you can basically identify, oh, that robot's on my team, I don't need to worry about it. That robot's on the other team, I should go try to tag it. And then this is basically how you're going to use this. So I'm going to develop a class called example state that basically inherits from robot state. That's going to design my own algorithm. And I'm going to have a class that says example policy that's going to inherit from robot policy. The two important things that you need to leave in are this super method. Basically, this is going to initialize the base class after you initialize your own class. So just leave this line right here, super.init at the very top with all these same arguments. And the same goes for the robot policy. And then your policy is basically going to say, send a velocity command. So the velocity command has two arguments. It's going to be the linear and angular velocity, so v and omega. And then you're just going to return that. The Robotarian provides sort of a unicycle controller for you already, which you're more than welcome to use. If you would like to design your own controller, please go ahead and do that. But basically, this is just a little helper method because the arguments for that code are a little weird. So you have to basically wrap things in an NumPy array, do the transpose a couple times, and then take the 0th element. Don't worry about this stuff. Just know that if you want to use the built-in controller, you can sort of have use this function right here that says, given the current pose of the robot and a waypoint that I want the robot to go to, get the velocity command to go there. All right, and then we basically have the game. So this is the game right here. And to start out, we basically need to do a couple different things. First, you're just going to construct the game. And the game takes a couple arguments, the number of robots we want to start with. For the actual game, you're going to use 12, but right now I'm just going to use 2. And the maximum number of iterations that the game can go through. Right now, I've just set this to 1,000, which is roughly 30 seconds. For the actual game, we'll do roughly like 3-minute games and count up points to see whoever wins. And then we're going to register 2 different teams. So obviously, when we start, you're only going to be developing code for your own team, which is totally fine. But basically, as we go through the day and tomorrow, we can have different teams face off against each other. You can work directly with a team, or you can message me and we can have teams work against each other and sort of see how your algorithms do in simulation. And that'll basically give you feedback to continue to develop your algorithm before you actually want to submit and try to see what happens on the actual robots. But basically, I need to give it 2 arguments. I need to give robots state objects, robot state classes, excuse me, as the first argument in a list. And then I need to give it a robot policy. And then the orange team is going to do the same. And there's 2 functions that we need to call. The first is game.setup and then game.run. So actually, I need to run all this code first. And then let's run the game. So the game's going to take a second to run. And what's going to be really important for you as you develop your system is a few objects that are within game. And one of the important ones is game.stateHistory. You can see we ran for 1,000 iterations, and state history has 1,001 frames. For each of these frames, you're going to have the state of all the robots in the system. So you're going to have your team's robots and the other robots, which is totally fine. Like if I go to type right here, these are going to be of type. Oh. These are both of type list. Oh, I need to go there. So if I go to the first element in that list, it's going to be one robot state. If I go to the other, it's going to be the other robot state. This is basically going to be a history of all the robot states over all the iterations. So you're going to basically be able to use this to get data and operate on it. And then we have this function that's basically going to animate the game for us. There's an argument here called fidelity. If you set fidelity to 1, it's going to basically draw every single frame that happened during the game, which is super smooth, but it takes like a minute to get you an animation. If you set it to 5, it's going to say draw every 5th frame. And so it's going to be a lot faster to render. And basically, this is going to still take a couple seconds, especially since I'm running this for the first time. But here is the game. I need to zoom out slightly. And we have little play controls so we can see what happened over time. And since we just gave it a blank policy and a blank state, the robots aren't going to do anything. So we need to do something about this. So let's see. So the first thing I'm going to do is I'm just going to copy both of these. Let's see if I can get this to work in a couple minutes. I'm going to develop offense state. And just because we're tight on time, I'm going to cheat a little bit and use my solutions. And basically, I'm trying to model for you guys how you can modify both the state and the policy in order to develop your own algorithm. So the first thing is I want to modify my policy. And what I want this policy to do is I want to drive it to drive to one of the flags. And I want it to basically capture the flag and then go back to its own side. So I'm going to say, I know where one of the flags are already. So I'm just going to type it manually, but you ideally are going to use the observation to figure out where a flag is and then try to control your robot towards that flag. So I'm going to say I'm going to have a few waypoints that I want my robot to go to. And the first is the flag, which is at 1.5 x, negative 0.75 y, and 0. And then once I capture the flag, I need to get back to my side. And my side is basically x is less than 0. So I'm going to go to negative 0.2, 0.0 y, and 0 heading. These are basically heading commands. You could also command it to a point, but that's beside the point. And then for my state, I basically need to keep track of which waypoint I want to get to. Remember that this policy doesn't store any state itself. It's storing this waypoint information, but I don't want to put any variables in here like, the waypoint index I want to go to. It shouldn't be stored here. It should ideally be stored in my robot state. So your robot state doesn't need to only include basically physical state information. It can also include state that you add to it or information that you add to it. So you could even say, add like the last 3 positions that the robot has been at in order to do this. And then we basically want to get a velocity command. So what I'm going to do is I'm going to copy a line that I have over here. And what this is basically going to say is, this is just fancy for saying if my position, I'm using this because I'm prototyping, is within 0.1 meters of the waypoint, I have this function that I can use called self attempt tag function. And I just need to operate on the state. So I need to pass in my robot state to this tag function. And then the game is going to take care of attempting that tag. And then I'm just going to say state waypoint index. So this is the waypoint index that we defined up here. Equals, I want it to not, I only want it to increment 1. So I don't want it to skip and try to get an out of index error. But then I'm going to say state waypoint index plus 1. And then I'm going to say velocity command equals self get vel command. And I'm just going to put in state dot pose and self waypoints state dot waypoint index. And I've lost my hop-in screen, but there we go. All right. So we are right at time, so I can just get this and show you guys what happens. I'm going to update. I'm going to stay on the purple team. I'm going to use now the offense state for this robot. and I'm going to use the offense policy. And now let's see what happens. Oh, it worked. Okay, awesome. Doesn't usually work on the first time, so don't be discouraged. Also, please excuse any bugs in the code that I've written myself. Yeah, let's see. So this is going to show us what happens, basically. And I know we're running late on time, so a few more details, basically. I'm going to send this collaboratory to the Discord. If you go to the robotics-mentor channel, I'll send all the information for how to duplicate this notebook. Here we go. There we go. So this little robot says, okay, I'm going to go to my first waypoint. And that first waypoint is this flag right here. And it's going to take a second. There are velocity limits on these robots, so you can't just say like, they're good. So it got to the waypoint, it captured the flag, so it grayed out. And now this guy's just not doing anything. It's not really, it doesn't really care that the flag was captured. It gets to the other side and whoop, point for purple. So now what you guys can do is you can try to design a policy for this that says, okay, try and find where the purple robot is and capture it, basically tag it so that they can't get the flag. And in the actual game, we'll basically use 12 robots. And so what that looks like, oh, I did something bad. You must provide, oh. So when we do actually do sort of a 12 robot game, you're going to need to define, this is going to be funny. You're going to need to define basically 6 robot states and robot policies. Now you don't need to design like 6 individual different states and 6 individual different policies. You can just define one and say apply to all of them. Or you could say like, you know, have 3 robots be defense, 3 robots be offense. It's totally up to you. And then let's just see what the results of this are. This is going to be super wacky. They're all going to try to go to the same flag. And I made the iterations short. But this is basically what the game will look like when we have 12 robots in the game. So I'm totally running over time, but a couple more details. There is a function within the system that's going to prevent collision. So basically, when we run it on the physical robots, we don't want robots to actually collide. The tag is going to be virtual. So what's going to happen is there's sort of a built-in functionality called a control barrier function that's going to prevent the robots from crashing into each other. Now, if you're prototyping and you want to turn that off, you totally can just for debugging purposes. And the appropriate argument for that is going to be use barriers false. So this is going to turn off the collision avoidance system such that you can see what your robots do in the absence of collision. So robots are basically going to drive between each other. That's going to be totally fine for prototyping. We're just going to we'll need to turn that back on when you're actually running on the system. Now, while that's running, I'll just show you the last sort of rules slide. Basically, you know, the idea is you guys play against each other as you're developing your algorithms. Totally a friendly competition. There's no like prize. This isn't like associated with the actual hackathon like prizes. You can basically use any member of any class when prototyping. But when you make a submission, I'd encourage you to not use the state._pose method. I'd like you guys to develop your own sort of state estimate and try and estimate the state of the robot, maybe based on where the flag locations are or based on some other information. And don't use the game state. The game state is going to store information about the other team's robots and stuff like that. You can totally look at that while you're prototyping. Just don't use that when you're actually submitting your code. A few rules. The tag cooldown right now is 3 seconds. The tag radius is 0.25 meters. So if you're within that sort of proximity with another robot and you hit, I'm going to try to tag them, they'll be tagged. We might need to tune that a little bit, but for right now, that's what it's set to. The number of robots is 12, 6 per team. So basically, you need to provide 6 robot states and 6 robot policies. Those can be the same class, or they can be each different classes. So you can develop 6 different algorithms, or you can develop one singular algorithm that drives all the robots. For now, we're going to play for 3 minutes, and that's going to be 5,400 iterations. Now, animating that in the Colab notebook is a little painful. So what you can also do, yeah, here we go. So this is going to give you a sense of what happens when these robots get near these robots, because you can see they're on a collision course. They start to move out of the way because these robots aren't sending a velocity command. The barrier certificate's going to say, oh, it's really going weird. Because basically all these robots are trying to go to the exact same point. All the robots can't be in the same point at the same time. So they're kind of like, they're freaking out a little bit. These guys got away, so whatever. Then what you can do for a longer animation is you can go, you basically take this return from the plot game object. You're going to say save and just do test, do MP4 for a video. And then, yeah, this little bit of code right here is going to let you download it. So if I do from Google Colab, import files, download, test MP4. Oh, and also the important part is, I totally forgot this. Because of the nature of this being online, you can have multiple team members in this notebook writing code at the same time, and you can all see the same output. Sorry, that's why I tried to put this in a Google Colab. So your team basically isn't distributed and trying to do, 4 different or 5 different versions of the code at once and then combining it. You can all write your code in the same notebook and look at what everyone else is writing and sort of help each other as you're developing it. But yeah, so any questions as I remember sort of any details that I've forgotten? I will send this all into the Discord with like more details about the logistics of submitting to the actual Robotarium. If you want to use the Robotarium for something else, say you're like, I don't really care about capture the flag, but I want to write like a completely different multi-robot system algorithm, you are totally welcome to do that. Basically, just go to the Robotarium website, look at the API they provide directly, and use that, and then I'll help you guys with submitting that to the Robotarium and getting the result of that code back to you. But yeah, overall, I'm here all weekend, so I actually don't know how you contact me in Discord. My username is Wattbot. I think you could probably use that to find me. So yeah, happy to get on calls with people if you guys need help throughout the hackathon. But overall, thank you guys. I hope you guys have fun. And I'll send all these resources to the Discord. If you're very eager, here is the slide deck. And here is the notebook where you can directly start coding. So if you open that notebook, you don't need to install anything. You basically just need to run all those cells. Oh, while I still am sharing my screen, what you'll need to do when you open this is go to File and save a copy in Drive, and then thank you. Share the new link with your teammates, and then that's the notebook that you and your teammates can edit and work inside of. You're going to have to work with like the sharing settings up in the top right corner to like invite your teammates and get them to be able to have edit access to the notebook. But yeah, this should get you started with like how to write things. As you guys have questions, please message me in Discord. And definitely, if you're interested, go to the actual sort of GitHub repo to see how this code is operating. If you go to RPS and capture the flag, this is basically all the code that's running the capture the flag game. So you can see here the robot state, the robot policy, and the robot observation. And then this is the CTF game. Don't judge me, my code is really bad because I wrote it very quickly without care for quality. But this code is what runs the game. So if you find bugs, it's probably in here. If you want to modify something, you're more than welcome to. Maybe talk to me first so we can like figure out what you're trying to do and see what the best way to do that is. But yeah, thank you guys for coming. Cool. So I'll be in Discord. Feel free to message me there. But bye, guys.